Okay.
So we're very happy to have Lotte Hollands from Heriot-Watt, who will give us an introduction to spectral networks.
Yes. Thank you very much for inviting me over here. It's really nice to be in India for the first time. This is actually just the title of the first talk, because so what I want to do in these two talks, today and tomorrow, I want to start out by explaining sort of the relation between Hitchin systems and quantum field theory, so n=2 theories. And what I will get to tomorrow is sort of explain sort of a new perspective on quantum Hitchin systems. So today, I'll basically introduce the notions that I will need for tomorrow. And so the plan of this talk is to start by giving a sort of very brief introduction from maybe a physics perspective, not being too careful about many details, Hitchin integrable systems. So the second thing I want to do is I want to relate this to n=2 theories in 4 dimensions. So in these in these topics, it turns out that sort of an important role is played by the notion of a spectral network. So that's what I want to introduce next. And I want to motivate that by saying a little bit about how one extracts the spectra of BPS particles from these spectral networks. And if I have time, either today or I'll do it tomorrow, I'll say a little bit about how sort of a mathematical application of these spectral networks, which has to do with abelianizing flat connections. So this is not the standard abelianization in the language, well, in the sense of Hitchin systems that you've seen before, but it's about abelianizing flat connections on a Riemann surface. Right. So let me start out with the Hitchin systems. Right, so in this talk and also tomorrow, I'll mainly fix on, to introduce a Hitchin integrable system, we need to choose a Lie group. And I will mostly be content with having SUK as a Lie group. We also need to choose a possibly punctured Riemann surface, which I call C. And then, so the Hitchin integrable system, or the Hitchin moduli space is the moduli space of solutions to some PDE, which I think Sergei has already introduced before, but let me just write them down again. So right, so it's the solutions A, phi of these PDEs where we fix some bundle, some G bundle on C, and where A is a G connection. In that G bundle on C, and where phi is an endomorphism, so that bundle I call E, it's an endomorphism valued 1 form. also known as the Higgs field. Right, and then, well, this Higgs field, it may have, since we might consider punctured Riemann surfaces, we have to specify what the behavior of this Higgs field is at those punctures. Right. So this Hitchin moduli space, let's call it M, it's known to have a hyperkähler structure. So M is equipped with, well, a natural hyperkähler structure. So what that means is that there is a P1, a sphere of complex structures, which I denote by J zeta. So I let zeta be the parameter parameterizing the sphere. And then there as well holomorphic symplectic forms, omega zeta, which are holomorphic for every zeta. Right, so this is the picture. So we have this P1 worth of, well, maybe let's get to this later. So we have this P1, which is parameterizing the complex structures of this moduli space. Now there are two special points. Zeta is equal to 0 and zeta is equal to infinity. So at zeta is equal to 0, this moduli space, this Hitchin, this moduli space to the solutions of the Hitchin equations, it can actually be identified with the moduli space of Higgs bundles. Which you've, as I've heard about quite a lot in the previous lectures. So they're given by tuples, the bundle with the holomorphic structure and the Higgs field. And as you've seen in previous lectures, at least which you've probably seen in previous lectures, is that there's a really nice map, which is called the Hitchin fibration, which sends any point in this moduli space of Higgs bundles to a point in a space which I denote by B, which will be the base of the Hitchin integrable system. And this map is given by sending this tuple, this Higgs bundle, to the determinant of X minus the Higgs field. Sorry? Yes. Yeah, it's diffeomorphic to, yes, that's right. So X here is just any coordinate. Well, it will become a little bit clearer later. So this gives, so this map gives this moduli space of Higgs bundles the structure of an integral system. Right, so So one way maybe to think about this base space B. So the base of the Hitchin integrable system is parameterized by these characteristic polynomials, and so any of these characteristic polynomials defines a curve. So setting this equal to 0 inside the cotangent bundle on C, where X is a coordinate in the fiber. So in Jacques notation, maybe in the previous lecture, I can spell this out at least for SUK as some equation. J x to the power k minus j is equal to 0. Where now these phi j's are differentials, so they're j differentials. Oh, sorry, yes, sorry. Start that with, yeah, yes. Right, so the point is that setting this characteristic polynomial equal to 0 defines the spectral curve. So every point in this base space corresponds to some kind of spectral curve, sigma, which will play a role in the physics, an important role in the physics later. Right. So I kind of assume that we've already seen a lot about Higgs bundles and about this integrable structure. So what I want to add to this is so there are more points in the sphere. So far we've discussed what happens at the North Pole. At the South Pole it's something similar, except that we get everything with a complex conjugate, so we get anti-Higgs bundles. But if psi is in zeta is in the complement of those 2 points, then there is a non-trivial statement, namely the non-abelian Hodge correspondence, which tells us that M zeta is actually the modular space of flat, and let's see, in general it's flat GC connections on C. So here we've complexified the gauge group G. And one way to see why this might be true is to start out with a solution of the Hitchin equation. So suppose we have a solution, a connection, as well as the Higgs field. And we take some value of zeta. Then we can form the following object. Yeah, I did introduce R before as well, I think. Yes. So we can define this object, and if you look at, well, it's easy to see if you look at the Hitchin equations, that this object is actually flat. So this is a complex, a a complex connection which is flat. Right. So, so the only things that I want to say about this Hessian moduli space is that, well, we've got this P1 of complex structures. At the North Pole and the South Pole, there is this structure in terms of Higgs bundles, whereas in the complement, this moduli space can be described as the moduli space of flat complexified connections. Right. So what is the relation to n equals 2 theories? So, there's a zoo of four-dimensional n equals 2 theories, and what Jacques just did in the previous lectures is he introduced sort of a very interesting subclass of n equals 2 theories, which were called the theories of class S. And yes. Oh, sorry. Yes. Right. Sorry. Yes, it is. So the way he constructed those theories of class S is to take this possibly punctured Riemann surface, to choose a Lie algebra, and to choose some data at the punctures. In his talk, that was related to these nilpointed orbits. But in general, it could be more general than that. So I'll just denote this by the letter D. So D for me encodes all the defect data at the punctures. And so I will denote any so given any punctured Riemann surface, a Lie algebra and some defect data at the punctures, that corresponds to a certain four-dimensional n equals 2 theory, and I will denote that theory by T, G, C of D. There are no twists in this. Yes, yes. So maybe I should go back to the comment that, well, I mostly think about SUK in this talk, so I will.
No, but there is a twist.
Sure, I'm not going to talk. Yeah, yes, that's right. That's right. That's right. That's right. So what he also what Jacques also mentioned very briefly is that these theories, these four-dimensional theories, have a six-dimensional origin. So there is a six-dimensional origin, which is the six-dimensional 2,0 theory. So there is a sort of mysterious six-dimensional conformal theory, which is called the six-dimensional 2,0 theory. It's labeled by the choice of a Lie algebra. And so this lives in 6 dimensions. If instead I put it on a Riemann surface C, so I consider it in a different background, I consider it in the background C times R3,1, then the statement is that this, and I consider appropriate defects at the punctures, then the statement is that this gives me back the theory T, G, C, D. Yes. It's the amount of supersymmetry that this theory preserves. Yeah, yes, it's some notation for supersymmetry. Yes, that's right. Yes, probably Jack can tell more about that. So maybe another way to say this is the theory that lives on M5 branes. So in string theory, there are these objects called branes. In M theory, we have the M5 brane. And so the world volume description on these M5 branes is supposed to be this particular 6-dimensional 2,0 theory. So we don't know too much about that on its own, but if you look at it on sort of special backgrounds, then we can say quite a bit about it. And in particular, we can argue that if we consider it on the background, the Riemann surface times R3,1, that it reduces to the theories that sort of Jacques introduced in a different way. Yes, it could. I'm not sure what the result would be. It could definitely be fibered. Yes. Yes. Yeah. That's yeah. Yes.
So if I assume what the other people the 4D theory that they got, each counting varies at different points.
Probably it needs to be fibered in sort of a nice way in order to keep some supersymmetry. There was another question. How do you get the? So what Jacques didn't really discuss is that there are sort of different types of 4-dimensional theories. So there are 4-dimensional theories which which are conformal, and they're the ones which are asymptotically free. So that means that they have different sort of behavior if you vary the gauge coupling. In Jacques' talk, he only discussed the conformal ones. And for the conformal ones, this defect data is basically given by these Young tableaus. So it's given by these nilpotent orbits, as he described it. But it could be, yeah. So I'll give you some examples later, from which you might get some idea of what.
The reference is some semi-simple deformation of a nilpotent.
Yes. I'm not sure whether there's sort of a definition of this defect data for all possible theories, but we'll see some examples later, which give you some idea. Sorry? Uh-huh. 3-1. Yes, that's right. Yes. So these defects that you need to add, they are points in C, but they cover all of R3,1. Yes. So Jacques also briefly mentioned that, so if you consider these theories T, G, C, D, that if you consider them in the low energy limit, that there is a sort of modular space of vacua. So there's there's part of the modular space that I'm mostly interested in, which is the Coulomb modular space. So this is basically the family of all the Coulomb vacua of these theories. And so the statement will be, which I want to argue next, the statement will be that this Coulomb modular space is really equal to the base of the Hitchin integrable system. So this is the Hitchin integrable system with gauge group G and base curve C. And so I should also, since we talk about punctures, I should mention that this is maybe a ramified Hitchin integrable system. Okay, so how can we argue for this? Or am I going to do this now? Sorry. Oh, wait, sorry. Right, so this statement is actually, let's see. Yeah, so sorry. I'm going to argue for a different statement a little bit later. So this is just a statement that the Coulomb modular space is equal to the base of this Hitchin integrable system. And that is sort of the earlier work of Donaki and Witten. And it's not so hard to see. So if you want to, well, but I'm not sure whether, let's see. Sorry. So if these theories, so in some cases, these four-dimensional theories, they have a Lagrangian description. A Lagrangian description in terms of gauge fields and an adjoint scalar field. And in those cases, you can easily see what the Coulomb vectora are. The Coulomb vectora are really the points where the potential part of this Lagrangian is equal to 0. And that will specify exactly this equation, this particular equation, for this adjoint scalar field. Right, so I didn't want to say too much about, well, okay. Wait, sorry. I'm going to say this a little bit more clear later, I think. So let me just leave this as a statement here and maybe explain it. I'll explain it later in some more detail. What I did want to say is that, okay, so we have this identification, and then this spectral curve sigma is identified with something that is very familiar from this four-dimensional perspective. It's namely the Sybek-Witten curve. And then there's another object that plays an important role, which is lambda, which is it's the tautological one form on T star of C when pulled back to C. And this one form, this differential, is known in physics as the Sybek-Witten differential. So this also plays a... Sorry? Oh, sorry, yes. Yeah, so sorry, so I just wanted to make this as a claim at the moment. I'll explain it a little bit later, but what I want to say is just how to go from the math of these Hitchin systems to the physics. So it's the sigma, the spectral curve, which is in physics known as the Sybek-Witten curve, and it's this one form which is known as the differential. So then, right, so T-dualize the four-dimensional theory. That's right, yeah.
I mean, the Higgs branches are hypercalar. The base of the Hitchin fibration is complex.
That's what we're going to do later. I think, yeah, you'll need to wait for a couple of more minutes to answer, to be able to ask your question. Right, so yeah. So we're still in the sort of remit of four-dimensional theories now. So what I want to say is, so suppose that we have this picture of having the spectral curve as some ramified covering over the Riemann surface C, then, so in physics, as sort of Jack discussed, C has all the sort of microscopic information that you need to know about this theory. About this four-dimensional theory of class S, whereas its cover, the Sybek-Witten curve, has all the low energy data. Of the same theory of class S. So whereas in the sort of 90s, people mostly sort of worried about this Sybek-Witten curve and discovered various properties about it. So the new sort of statement by Gayotto and more Nijtske Gayotto about 10 years ago is that you should really see this the Sybek-Witten curve as a covering over C, and this C contains all the data that you need to construct this four-dimensional field theory. Right, so examples of this low energy data, so that will come next. So one of the things that you can get out of this covering, out of this Riemann surface, is the BPS spectrum. Of particles in this four-dimensional theory of class S. Uh-huh. That's right.
Choosing a projection from other curve.
Yeah, yes.
There's an orthogonal curve, it's giving extra data.
That's right, yes, yes. Yes, that's exactly right. Yes, yes. So some of the other things that are computed by this or encoded in the Sybek-Witten curve is what is known as the prepotential. So if I consider, well, I'm not sure whether I want to say too much about it, but if I take a basis of A and B cycles on the Sybek-Witten curve, and I consider the periods along these cycles, then this tells me that the prepotential is obtained as in terms of this formula. And yes. That's right. Yeah, yes, yes, yes. Right, sorry. So what I want to... Okay, so what we've seen so far is that if I take this four-dimensional theory of class S, then it has a branch of vector, the Coulomb branch, and all of these vector are in one-to-one correspondence with points on the base of the Hitchin system. Yet, we haven't seen the complete Hitchin integrable system yet. I mean, we haven't seen the complete Hitchin moduli space yet. So that complete Hitchin moduli space only arises if we compactify to 3 dimensions. So let me say that. So the total space of the Hitchin integrable system only comes to life when we reduce this theory on a circle. So that is, we want to place this four-dimensional theory on R2,1 times a circle of radius r. Now, if you look at energies, which are much smaller than 1 over this radius r, then this theory, the effective theory on R2,1, will have a description as a sigma model, as a three-dimensional sigma model into some modular space. And we know that that theory, that effective three-dimensional sigma model, needs to have n equals 4 supersymmetry, which says that this modular space, the target space of the sigma model, needs to be hyperkähler. It turns out that that modular space for these particular theories of class S is the Hitchin modular space. And to argue that, you can consider the following sort of clever argument. So remember that these four-dimensional theories of class S, that they have a six-dimensional origin. And often this is denoted by these letters. Now, what I said before is that if we consider this six-dimensional theory in the background C times R3, 1, then we get a four-dimensional theory on the remaining four-dimensional directions. And that four-dimensional theory is a theory of class S. What I argue then is that if we look at this theory on a circle, where we make that circle to be very small, or we consider this theory at energies smaller than 1 over the radius of that circle, then this has a description as a 3D sigma model into some hyperkähler modular space M. But we didn't know yet what that hyperkähler modular space it was. We just knew that it was hyperkähler because it has n equals 4 supersymmetry. But now I can do something different. I can start out with the same theory, but instead compactifying it on the circle first. And we don't know much about the six-dimensional theory, but one of the things that we know about the six-dimensional theory is that if we compactify it on a circle, it becomes something well known. It becomes a five-dimensional Young-Mills theory. At least in the low energy limit. So now that we've got something well known for which we can write down a Lagrangian, for which we can do sort of all the conventional physics, for which we have all the conventional physics methods, we can reduce it on this Riemann surface C. And this had been basically done in sort of a different context a long time ago by Brzezinski, Johansson, Saurav, and Vafa, and also by Harvey, Moore, and Ströbinger. So what they do is they start out by writing down the Lagrangian for this Young-Mills theory, and then put this Lagrangian on the background C times R2, 1, and then make the directions along this Riemann surface very small. So what you see is then that the Lagrangian becomes that of a sigma model into a modular space, where that modular space is given by, so this becomes a 3D sigma model into a modular space. Where that modular space is a space of vacuum configurations of that five-dimensional Young-Mills theory. Which are translationally invariant in these remaining directions. And those vacuum configurations are exactly described by the Hitchin equations. Let's see. So what do you need to do? You need to be able to write down this Young-Mills with the defect operators.
Yeah, and the defects wrap the S1.
That's, yeah, yes.
And, I mean,
I haven't, yeah.
In the old days, when people did this back in the day, I don't think they were doing it with these defects.
No. The papers that I was referring to, they do it for the closed curve. That's right. I wonder how difficult it is to,
Offhand, I'm not sure I know how to carry it all over.
Yeah. I don't think I've seen it being done in all detail. But yeah, presumably it can be done. Right. So this is a rough argument that at least works for closed curves, but presumably also as a generalization to punctures. That's right. Yeah. So I'm ignoring these subtleties. That's right. Yeah. Yes. They consider it topological. Yeah.
If you go to a partial twist, I think magnify that breaks all of this.
Oh, no, but what I'm saying is not obvious that this partial twist.
Probably you can argue that. Yeah. Since you're studying it on C times, well, so they studied it on C times R2. I don't think there are many twists that are available in that setting. Yeah, but that will be maybe something to think about as well. Sorry, say that again. So if any theory...
So what you've shown here is that if we take this and put two theory which descends from the 60 theory, then compactifying that on a circle should give you the Hitchin moduli.
Yes.
If
Yeah.
say that, okay, like compactifying this on a circle gives you the Hitchin moduli.
Yes. Yeah. I think so. Yes. Okay, right. So I think that concludes the sort of the brief argument that even the complete Hitchin moduli space plays a role in gauge theory, but it plays that role in the theory if you compactify it on S1. Yeah, so that's what we just argued. So from this argument, we only got that it is a 3D sigma model into a hyperkähler moduli space, but by going this way, we see that M is actually the moduli space of solutions to the Hitchin equations. Right. Right, so then I can now introduce this notion of a spectral network, which will help us, for one thing, to be able to enumerate all the BPS states in these four-dimensional theories of class S. Great, so we go back to our four-dimensional theory of class S. So I'm not compactifying it on the circle now, I'm really staying with that four-dimensional theory. And I'm fixing a phase and I'm fixing a Coulomb vector. Which is a point in the base of the Hitchin system. So it's given by a characteristic polynomial. And now I'm writing my characteristic polynomial in a different way as before. I'm writing it as a product of x minus k1 differentials. So this is just something which is equivalent to writing it in terms of k differentials, but that will be better for what I want to do next. So these lambda I are meromorphic one differentials on C. Sorry?
They don't really exist. They're quite really fast. It's a symmetric function. The order of the lambda.
Sorry? With?
There are no global lambda.
There are no global lambdas. Oh, I see.
General spectral coverage, you reduce
That's, well, okay. Yeah, I guess, let's see, that's not, okay, let me think a little bit about that, yeah. Let's just do it locally then, for the moment, yeah, yes. So, so the spectral network is a set of trajectories on C, real trajectories, and these trajectories, they are determined by a condition. And that condition says that lambda I minus lambda j contracted with a tangent vector to that trajectory should be real valued up to some phase. So V is for some I and j. So I get a set of trajectories on the curve C, which are labeled by I and j, for which this condition is true. But let me, yeah. So what I want to do now is to explain this in the simplest example, where k is equal to 2. So let me perhaps do that. No. Oh, sorry. Yeah. So I didn't write that down very clearly, but I say that the spectral network is made out of trajectories, and these trajectories are defined by the fact that this equation should hold. This inequality. This equation should hold for every tangent vector to that trajectory.
That's not all right. There's no condition. It has to start out from the.
Yes. That's right. That's right. But let's go to this.
All the factors express lambda, that you multiply the matrices and you are cancelling the forms. So lambda is a matrix of one form.
It's just a one form, because I'm taking the determinant.
What does the product mean in this case? Like, since the things in the bracket, they are just matrix on one form.
So locally think of this spectral curve as a k-fold covering over C. So these lambdas just describe the covers of that spectral curve.
It's a one form, right?
Okay. Maybe just say, well, so locally we restrict the tautological one form to the sheets of the covering. So in particular, I could choose a trivialization of my covering, and then I can just really define lambda I as that restriction. Okay, let's go maybe to the simplest case, where k is equal to 2, where we don't have many of these issues. So in that case, the spectral cover is given by the equation x squared minus phi 2 is equal to 0, where phi 2 is a quadratic differential. And so this condition for a trajectory to be part of the spectral network boils to the condition that if I contract the square root of phi 2 with a tangent factor, that this is real up to a phase theta. And this condition is a very well-known condition, so given any quadratic differential, looking at trajectories which satisfy this constraint determines the foliation of your Riemann surface. So this is a foliation determined by this quadratic differential. It's a singular fibration. Namely, it's singular at the zeros of phi 2. So in order to see that it's a fibration, I have the same problem as Jack. I think I said it. Sorry. It's a singular foliation. So to see that it's a foliation, sort of on any regular point, just take a regular point C0 on your curve C, and then you can introduce a new coordinate. You can introduce as a coordinate W, which is equal to the square root of, you can introduce a coordinate which is the integral from C0 to some point in the neighborhood C of the square root of phi 2. In terms of this coordinate, this condition just reads dW is equal to the square root of phi 2. So in terms of this coordinate W, this foliation is just a foliation of straight lines which have inclination theta. So all the trajectories are the lines of inclination theta. Right, so if you look at the neighborhood of a simple zero, of the quadratic differential, then you can easily see that this foliation is indeed singular. It's a sort of three-point singularity with three of these trajectories coming out of that simple zero, and the foliation being regular everywhere else. So, right. So now we've defined sort of a foliation given any quadratic differential. To get to the spectral network, we only take a subset of these trajectories. Namely, we only take the trajectories. Maybe I'll say it in Word because I'm running out of time. So to define the spectral network, we take all of the trajectories which start or end at these simple zeros. So the collection, the union of all of these singular trajectories, that defines our spectral network. And so the other two things that we do is we attach an orientation to all of these singular trajectories. So the orientation will be outward from these simple zeros. And then we also add a tuple of numbers to these trajectories. In this case, it's either 1, 2, or 2, 1. And whether it is 1, 2, or 2, 1 depends on which trivialization of the covering we use. So, for instance, in this case, suppose that we choose the branch cut over here. Then we can ask ourselves the question, is this square root of phi 2 contracted with v, which is outward along this trajectory? Is it positive or is it negative? And depending whether it's positive or negative determines whether it's a 1, 2, or a 2, 1 that we assign to this line. So for one choice of trivialization, this will be the result. So that collection of data determines what the spectral network is. Right, so maybe some remarks for what happens for higher k. So if k is larger than 2, a few things change. Well, so this condition that we had here depends on I and j in general. So for k is equal to 2, it can only be 1 or 2. For higher k, it can be any I and j smaller than k. And that means that all these trajectories that we get, that they will be labeled by these numbers, by these tuples ij or ji. So whereas for k is equal to 2, this constraint determines the foliation. For higher k, it doesn't determine the foliation on C anymore. Instead, what can happen is that, for instance, a trajectory with label 1, 2 intersects with a trajectory of label 2, 3. And what may even happen is that there is another trajectory which is born out of this intersection of these two trajectories, which then has to carry the label 1, 3 in this case. Sorry. If the labels were like this, then it had to carry the label 1, 3. Always appear? Whenever they can, they will appear, yes. Yes, that's right. Oh, yes. Oh, sorry. Yes, right. It's on the base B, yes. Sorry, on the base C, yes.
Sorry, are these on the basis of Hitchin complex space, or are these
on C? These are structures on C. It's yes. Not quite. I mean, there are walls on the, yes. I was hoping to come to that later, yeah. Yes, that's right. That's right. Yes, as a fixed point, I have a fixed spectral covering, and the spectral network is some structure on the base of that covering. Right, so, yeah, let me give one example. So suppose that our curve C is just equal to the complex plane, or maybe you should rather see it as P1 minus infinity, because there will be a singularity at infinity. And we consider a quadratic differential, which is just equal to c squared plus 2m, where m is some number. So in terms of a Hitchin system, this means that it's an irregular singularity at infinity. This differential has an irregular singularity at infinity. So suppose that we fix this constant m to be larger than 0, and suppose that we fix our phase to be slightly positive. Then the corresponding spectral network will look as follows. There will be two simple zeros of this quadratic differential. There will be 3 of these singular trajectories coming out of each of these zeros. they will all have orientations. And if we choose a branch cut, so if we choose a local trivialization of the covering, then they will carry some labels. Right. Now, what I can do is I can change this phase. So this phase, I chose it to be slightly positive. If I'm going to make it bigger than 0, then the topology of this network will stay exactly the same. But if I will change it to be equal to 0, so if I make it smaller, then let's say theta is equal to 0, these two trajectories, this one and this one, they will start coinciding. And what I will get is the following picture. I will get a saddle trajectory in between those two branch points, in between those two zeros. If I make theta bigger again, sorry, smaller again, so if I have a negative theta, then it will go the other way. Oh, sorry. What is the other way? This one. We'll go like this. Sorry, what is the? What is the orientation? Yeah, so it doesn't have, well, there are sort of two of these trajectories which really overlap. So I'm drawing it with two orientations. Yes. Right, so this is what is called a flip. And so as I was hoping to explain, oh, well, I still have some time, right? Yeah. Okay, I might still be able to explain that this corresponds to, so this is a setup where I have some curve, I have some data at the puncture. So this defines a certain four-dimensional n equals 2 theory. This is really sort of the simplest example of a four-dimensional n equals 2 theory. It's a theory of just a single hypermultiplet and nothing else. And the hypermultiplet has this mass m. And exactly this flip of these spectral networks tells you that there is a BPS state, a BPS hypermultiplet present in the theory. The fact that there is this stable trajectory tells you that there is a BPS particle, well, of mass m. And I will say a little bit more about that in a couple of minutes, I hope. Sorry? Yes, that's right, yes. Well, sorry, I said I do have some minutes, but I only have 5 minutes, right? Or what is it? Oh, okay, right. I hadn't seen it yet. Okay, so let me do that quickly then. You mean, okay. It's a little bit tricky to do that, yeah. And it's tricky exactly because there's no canonical way of assigning one cycles on the cover if there is a pole of if there is a zero of higher order. But maybe we can talk about that, yeah. Right. So let me say a few words about BPS states. Right, so these spectral networks, they actually turn out to enumerate many kinds of BPS objects in this four-dimensional theory. And what I wanted to focus on here is sort of the simplest kind of BPS state, which is a 4D BPS particle. So 4D BPS particles, they're sort of really just one particle states in R 3,1 that preserve half of the supersymmetry. And whereas it's sort of, well, harder to explain them from a field theory point of view, in terms of this geometry of spectral curves, there is a very elegant description of them. So so in terms of the geometry of the spectral cover, so let's draw this spectral cover. So in general, a k-fold spectral cover, where I may have some branch points. I can think about filling in a disk in T star, in this cotangent bundle T star of C, which has its boundary at the spectral cover. So the boundary of this disk is some one cycle, which I call gamma, on the spectral cover. If I
on this zero section of star C. Yeah, but the spectral cover was on C, not on sigma.
Spectral curve. It's ending on the spectral curve, sorry. Yes. So I just think of a disk in the T star of C, which is ending on sigma.
Ending on
Yes.
what about the curve?
Sorry, yes. It's yeah, I all blame this on traveling.
I have no such excuse.
Sorry, this is a cycle? Yes, that's right. That's right. So far, it's topological. So maybe, maybe the good picture to think about this is where you think about the M5 brane picture, where the M5 brane is wrapping sigma as well as R 3,1, and then I can have M2 branes, which are wrapping disks in the geometry, which end on this M5 brane. And then in 4 dimensions, this only gives you a line, which is the world line of this particle. Now, if you just wrap a generic disk, then this configuration doesn't preserve any supersymmetry. So this disk has to be special in order for this particle to preserve any supersymmetry. And the condition that it preserves, that it's BPS, is the condition that the central charge is equal to the mass. And in terms of the geometry, the central charge of this particle is given by integrating the tautological 1 form along this cycle gamma, which I could also write down. So suppose that I call the projection of this the projection of this boundary to the curve C. Suppose that I call this I. Then I can also write this as the integral over this interval I of lambda I minus lambda j. Whereas the mass is given by integrating the absolute value of this difference. And then you see in order for this, so the BPS condition says that, so in order to preserve symmetry, we need to have that the absolute value of Z needs to be equal to the mass. And this can only be true if the defining condition for the spectral network is satisfied. Namely, if this lambda I minus lambda j contracted to some vector, contracted with some vector v is real up to some overall phase theta. Right, so the statement is that this spectral network exactly encodes BPS states because it exactly draws the trajectory for which this is satisfied. And in particular, also in this example, so we had this saddle trajectory where this. So maybe there's a lot of things. Let's draw this geometry. So what is this spectral curve here? So the spectral curve looks something like this. It's a fibration. It's a 2-to-1 cover over C. And sigma has one cycle, gamma, which is the cycle which goes along this tube. So we could fill in this tube we could fill in this circle with a disk, and we could wrap we could wrap an M2 brane over this disk D and get a particle in C. And the BPS condition then tells us that this D needs to be very special in order for this particle to be BPS. So in terms of this picture, the curve gamma is a curve that goes around these two branch points, around these two zeros of phi 2. And also I can draw it as well in these pictures. But if I go along these curves, then the condition is not satisfied, right? Because these trajectories diverge. Only for this critical phase, this BPS condition is satisfied if I go along this curve gamma. So that tells us that at this particular phase, this critical phase, there is a BPS particle in the spectrum of the theory. And it tells us exactly what the charge is, what the central charge is, what the mass is, and its electromagnetic charge is given by this one cycle gamma. So I think I need to stop there.
What exactly is the leaf of the foliation? That foliation.
Which one? This one? Ah, okay, right.
What is the leaf?
So these are the leaves. So these are the regular leaves.
Yeah.
This is the singular leaf.
I mean, what is the mathematical expression? It should be phi is equal to some constant. So what is that leaf? What are the huh? Well, has constant.
There are something that the BPS states correspond to intervals in the spectral.
To intervals in the spectral network between zeros or to subnetworks between?
That's at least the hypermultiplets are. Yeah. That's right. So those are some of the BPS particles. It can be more. For instance, well, for k is equal to 2, these are all the particles you will find. But if you go for higher k, then you could have a configuration like this. You could have three zeros, which are all of a different kind. So this is, say, of type 1, 2, this of 2, 3, and this of 3, 1. And then I could have a spectral network, which looks like this. It's some junction. So this corresponds if, well, there is a nice, let's see whether I can do this. No, not this. There is a nice one cycle on sigma that corresponds to such a network. And for that one cycle, the BPS condition is satisfied as well. So this will give another type of BPS state. And you can think of sort of more complicated versions of this with all kind of loops and so on. So yeah.
There is some full classification of possibilities.
I'm trying to see whether this is a sort of a mathematically rigorous classification of things that can happen. So I'm right. I'm not sure to what extent it has been spelled out, sort of how these networks can exactly look like. We've considered various theories, and we find various sort of networks of different kinds that produce BPS particles. But I'm not sure whether you can make the statement that any kind of network that you can think of actually occurs in some four-dimensional theory or.
Have found sufficiently crazy BPS spectra.
Oh yeah. Yes.
Particular points on the Coulomb graph that you would not want to play if you found all of the first one.
Yeah, so another example is the E6 example that Jack sort of mentioned, where you can also find sort of very crazy topologies. So yes, right. So I think it's probably true, but there is no mathematical statement that that really classifies all of them.
Yeah. So the main utility of spectral networks is to find BPS states which you couldn't see in the usual way of analyzing it using.
It's it's a very structural way of finding these finding the BPS states. So for many theories, these BPS states were known, but it was not known for any theory of class S. And so this gives you, given any theory of class S, you can look at its Coulomb branch, you can write down what the differentials are, and you can just go through the whole modular space, vary the phases, and find all these BPS states. So that's something that was definitely not known before. And so there are other techniques of finding these BPS particles as well, for instance, quiver techniques and so on, but they're not applicable to sort of any set. So this is really a setting. This is really a sort of a technique that holds for any setting.
So aside from BPS particles and states, is there anything else that we can derive from the spectral network?
Yeah, so there are many other things that you can derive from spectral networks. So you can place defects in your theory, and you can look at the BPS states that are preserved by these defects. So that's all encoded. So you can look at line defects, surface defects, and so on. Another application is sort of more mathematical, and that is this abelianization, which also uses the spectral network, but I'll say more about that tomorrow.
Thanks. Did you mean non-abelianization, or?
No, I mean abelianization. But
wasn't that like a math thing from Georgia?
Yeah, but in recent things that we've been doing, it turns out that abelianization is the more natural way of thinking about it. Yeah. But,
So, any other questions? So I actually had a question. You mentioned that the spectral networks saturate the BPS inequality.
So yes.
You mentioned that spectral networks saturate the BPS.
Yes.
And I was wondering whether graphs which are not spectral networks but labeled as spectral networks are, so with with the condition at collisions. Do they represent some non-BPS states in this theory? I mean,
that's a good question.
Over what space are you saturating the BPS inequality? When you said that the spectral networks are precisely those for which BPS.
Yeah, so you just draw some random sort of network that obeys a certain set of constraints, and you wonder whether that means anything physically. Yeah. I don't know.
So, I mean, there is a picture. So this is a comment/question. There's a picture involving A-brains. There's some work of myself and my collaborators, Hitchin, Kontsevich, and Kazarkov. So where you can interpret this generalization of spectral networks, where the edges are labeled by objects in some auxiliary category, which you can think of as a category of A-brains on some.
I see.
You assume you have some fibration over your surface. For example, if you have a spectral cover, you get a fibration over the cotangent bundle, which degenerates along the spectral curve. And this gives you a symplectic fibration over your base curve. And it defines a family of categories over your Riemann surface, whose fibers are the category of A-branes. And the contextual picture is that these general graphs labeled by objects of the fiber category are A-branes in the total space. And the analog of spectral networks are BPS A-branes. So I don't know if there some physical, I was going to ask you whether physical...
I'm not aware of that work. Oh, if we talk together, then there's an awful...
Yeah, it doesn't exist as a paper yet, but it's...
I see. Well, okay, so it's no surprise that I'm not aware. Okay, well, that sounds very interesting.
Is there any reason to expect these things to be related to A-branes in some...
Yeah, so these disks are actually special Lagrangian disks. So in that sense, yes.
And by hyperkähler rotation, they will be...
They're special Lagrangian on the nose, I think, yeah. So, Yeah. So that might be the relation, but
Is there a physical reason to expect some?
they're expected to be aberrants. No, I don't really know. I would need to think about that. Yes. Yes.
I don't remember my question.
You're
No, sorry. So I was going to ask, is there a quick way, once I know the spectral network,
to see if there are walls of marginal stability on the base?
To see where the walls of marginal stability are. Yes. So what happens at these walls of marginal stability? Right. So there's one thing that you can easily see, and that's where BPS states become massless. That's just where two of these where branch points come together. Walls of marginal stability. Well, you can see it because the network really changes its isotopy class in a certain So usually, if you just make small changes along the base, then the isotopy class of the spectral network will not change. But if you cross a wall of marginal stability, it will change. So yes, you can see that as well. Yeah, so the next example that I was going to do is pure n equals 2, but time doesn't really allow me to do that. So but there you could, I'll need to see whether I can.
Any other questions? If not, let's thank Lotte again.